Welcome to the Explainer. Today, we are taking on an absolute beast of a topic. We're going to demystify distributed application architecture. If you've ever looked at a modern system and just felt completely overwhelmed by the sheer number of moving parts, you are exactly in the right place. My goal today is to take these incredibly intimidating, complex concepts and transform them into a clear, actionable toolkit that you can actually use. So let's dive right into this.
To kick things off, what better way to set the stage than with this famous warning from software engineering legend Martin Fowler? Back in 2002, he wrote the first law of distributed object design, which is simply don't distribute your objects. Now, I know what you're thinking. Technology has changed a ton since 2002. And, well, yeah, it has. But the core lesson here fundamentally remains the exact same. Moving from a single, centralized application to a distributed one isn't just some minor technical detail. It introduces this massive, inherent complexity that totally changes how your entire system fails. You literally have to design for it from the ground up.
So, here's our roadmap for today's Explainer. We're going to cover the distributed dilemma, essential architecture patterns, designing for failure, deploying to production, and finally, the microservice reality. Let's jump into Section 1. The distributed dilemma.
To really grasp the complex reality we're stepping into here, we have to first look at the comfortable, predictable status quo of traditional software design. On one hand, you've got your classic monolithic architecture. Think of it as a single blue box server with a static, well-defined IP address. It's cozy, it's predictable. But on the other hand, welcome to the distributed architecture. Suddenly, our application is broken down into all these loosely coupled services, stuff like pet API or pet inventory, running across multiple instances and identified by these massive, randomly generated UUIDs. As you can see, the complexity here has absolutely exploded.
And because we have all these instances flying around, we really need to talk about how they handle data. This brings us to stateful versus stateless components. A stateful component is one that creates or modifies persistent data, like your database. A stateless component, on the other hand, doesn't hold on to any persistent data at all. The absolutely crucial takeaway here is that stateless components are vastly easier to manage. If one crashes, no big deal. You can instantly tear it down and spin up a new one on a totally different node without losing a single thing. So, in a distributed system, you basically want to make as many components stateless as humanly possible and push those really hard-to-manage stateful components all the way to the edges of your application.
All right, moving on to Section 2, Essential Architecture Patterns. Let's see how we actually tame this complexity.
Now that we have all these loosely coupled components, the big question is, how do we get them to talk to each other reliably? In a monolith, Service A might just have Service B's static IP hard-coded right in. Easy. But in our new distributed world, Service B might hop over to a totally new node at any given second. To solve this hardwiring problem, Service A cleverly uses a DNS service. It works like this. Service B registers itself with the DNS. Then, when Service A wants to connect, it queries the DNS, acting as an external authority to find out exactly where Service B is currently hanging out. Just like that, we've eliminated those brittle, hard-coded configurations.
But hold on, what if Service B isn't just one instance, but say 10 of them? Well, that's where load balancing comes into play. If Service A sends a request, it gets intercepted by a load balancer. This load balancer takes the incoming traffic and distributes it equally across all the available instances of Service B. It usually does this using an algorithm called round robin, literally just going from instance 1, 2, 2, 3, and then back around again. This is awesome because it ensures no single instance gets totally overwhelmed, and it basically guarantees high availability for your whole system.
Which brings us to Section 3, Designing for Failure. Remember, it's a matter of when, not if. Working in a distributed system means you really have to shift your mindset. Like I said, it is never a question of if a component will fail, it is strictly a question of when. And that leads us to a pretty critical question. If our load balancer is just constantly firing traffic everywhere, how does it actually know if a specific instance is even alive? What if it secretly crashed 5 minutes ago? Well, the secret sauce here is automated system health monitoring. Load balancers will periodically pull your instances with health checks. They're essentially just knocking on the door asking, "Hey, are you still there?" The service will either respond yes, no, or it'll just totally time out. If the answer is no or a timeout, the system immediately steps in. It automatically kills that unhealthy instance and spins up a brand new replacement in its place. We call this auto-healing, and let me tell you, this is exactly the magic that prevents you from getting a blaring 3 a.m. pager alert when some random node decides to give up the ghost in the middle of the night. And that builds into an even more powerful idea, the circuit breaker pattern. Think about an electrical circuit breaker in your house.
If you plug in a faulty appliance, the breaker trips, cutting the power so your house doesn't literally burn down. We do the exact same thing in distributed software. If service B starts timing out, we absolutely do not want service A to just keep hammering it with requests, getting backed up and eventually crashing too. Instead, after a certain threshold of failures, our software circuit breaker trips open. Any subsequent calls from service A just fail immediately. It doesn't even bother trying to reach service B. This stops a massive, catastrophic domino effect of cascading system failures.
To round out our defensive toolkit, we've got bulkheads and rate limiters. Bulkheads are the super cool resilience pattern used to safely isolate system resources. They make sure that if one specific area gets totally swamped, it doesn't drain the resources for the rest of the system. Rate limiters, on the other hand, act kind of like nightclub bouncers. They control unexpected traffic spikes by strictly limiting the number of requests allowed in a given time window. Put these together with circuit breakers, and you've got an incredibly robust line of defense.
All right, moving into Section 4, deploying to production. We're talking zero downtime updates here.
Now we're really raising the stakes, taking all this from theory into reality. Because how do we actually update these hyper-complex systems without ever taking them offline? Two of the absolute best strategies for this are Blue-Green deployments and Canary releases. In a Blue-Green deployment, you've got your current Blue version running live. You deploy the shiny new Green version right alongside it. You run your smoke tests, and if everything looks solid, you just flip a switch and instantly route all traffic over to the Green version. A Canary release, though, is much more gradual. You funnel just a tiny percentage of traffic, maybe 1%, to the new version, watch it closely, and then slowly ramp it up. It's actually named after the old coal miner tactic, taking a canary into the mine as an early warning for toxic gas. If the release fails for that 1%, you just pull it back before it impacts everyone else.
Let's actually visualize that Blue-Green deployment real quick because it's so elegantly simple. Initially, your router is sending 100% of the live traffic to the Blue version. Let's call it 1.0. Meanwhile, your new Green version, 1.1, is fully deployed but totally isolated, just running its smoke tests. Once it passes, the router simply updates its config to point to Green. Boom! All traffic instantly flows to 1.1. And the real magic here? The instant rollback. If the new Green version suddenly starts throwing weird errors, you literally just reconfigure the router to point right back to Blue.
That's great for code, but what happens when you have an irreversible data change? Something like updating a complex database schema. You definitely can't just flip a router switch for that. Instead, you have to break this highly sensitive process down into 3 very distinct zero downtime phases. Step 1, you roll out a backward compatible schema change. Step 2, you roll out the new application code that knows how to use that new schema. And finally, Step 3, you clean up the old schema and safely remove that backward compatibility.
Notice the really careful, deliberate progression required here. First, the database itself gets updated to version 1.1, while Service A is still safely, happily running on version 1.0. Then, the application code for Service A is bumped up to version 1.1 to match it. Only then does the database run a final cleanup to reach version 1.2. By strictly separating the data changes from the code changes, your system remains completely online and operational throughout the entire migration process. It's brilliant.
And that brings us to our final section, Section 5, the microservice reality. Just to summarize the modern landscape for a moment, modern microservices give us immense, incredible agility, but they absolutely require advanced patterns to stay manageable once you scale up. You've got the API gateway, which acts as a single, highly secure entry point for all your clients. You have the Saga pattern, which is fantastic for managing distributed transactions without locking up your entire database. There's CQRS and event sourcing, which help optimize read and write scaling while giving you absolute, perfect auditing capabilities. And then there's the Strangler pattern. This one lets us gradually migrate, or strangle, legacy monolithic systems piece by piece, so we never have to attempt one of those massive, highly risky overnight rewrite nightmares. Which leaves us with one final, pretty critical question for you to chew on, because the reality is often quite a bit messier than these clean diagrams. Take a hard look at your architecture and ask yourself, are you building true, independently deployable microservices, or have you just accidentally built a distributed monolith? Because I'll tell you right now, a hard-coupled distributed system combines the absolute worst disadvantages of both worlds. You get all the nightmare complexity of distribution with literally none of the agility. So think carefully about where you draw those boundaries. And that wraps up today's explainer on distributed application architecture. I really hope this gave you a clear, structured lens to look through the next time you sit down to design a system. Stay curious, keep learning, and I'll catch you in the next explainer.